Hello, everybody. Thank you very much for coming today. So we're gonna talk a little bit today about the labs of the future and certain things that Celgene is doing within life sciences. So we have an agenda we're going to work off of today. We've got a few introductions we want to do, and then we're going to move into two phases. One of them is going to be how we integrate AWS in the laboratory space, and then the last example is using digital pathology to see what we can do with this technology. So today with us we have a very early adopter and a long-term customer of AWS, Celgene. They're currently storing and processing and analyzing about 20 petabytes of data. They're working on three major R&D initiatives with us. One is the Melanoma Genome Project. The other is around computational chemistry, and then AI workloads. They've recently done a merger with another very long-term and good customer, Bristol Myers Squibb. This new company hopes to become the leader in biopharmacy. So today we have two speakers with us. One is Lance Smith, who's Director of R&D Cloud and HPC. And the other is Pascal Starnik, who is Senior Director Translational Computation. So both of them are long-term IT professionals and research scientists and come from the Celgene side of the world. So what are we facing today, and what are the challenges that these labs are facing? And we've kind of broke it into four parts. One, we see a bifurcation of the data between the wet lab and the computational space. But in reality, this is a unified workload that needs to be data-driven. So you'll do your research in your wet lab, then you'll run it through different instrumentation, and this instrumentation produces large amounts of data that we then have to then analyze and run. We have found that we've gotten most of the low-hanging fruit that we can get. And we need to move to more challenging targets, and we need to come to the concept of a batch size of 1. So there's a need for data-driven techniques that's just then using that data to optimize these workflows. And then finally, we have multiple streams of data coming in, and that needs to be combined and then tagged so it acts as one cohort. And what we're hearing from the organizations is that we have kind of four major problems or major challenges they're also facing. We have an inability to aggregate and share this data we're collecting, both internally but also with the researchers and peers externally. We then have these data streams coming in. We need to combine them, and then more importantly, we need to tag them and catalog them so we can actually make them actionable, and then ability to go back and do look-backs so that when we were looking for different methods or different paths of research, they're there to search for. These workflows, unfortunately, are not optimized. Especially when it comes to some critical lab equipment, and much of this lab equipment has very large capital investments with it. And then the thing that I think as people and as employees we find most troublesome is the repetitive low-value manual tasks that these researchers have to do every day, in and out, in and out. That if we can actually move some of these tasks in an automated fashion and take that workload off of them, it allows them to do what they actually got into science to do and actually understand research. So the first thing we're going to kind of move into is we want to look at the cloud integration and how we've integrated these labs with that. And with that, I'd like to hand this over to Lance.
Thank you, Sam. Good afternoon or good evening, everyone. My name is Lance Smith. I'm from Celgene, now part of the BMS family, so we're excited to what the future holds for us. We are a global pharmaceutical company, primarily specializing in oncology and immunology, and we span drug discovery to clinical to manufacturing and sales. So it's a really challenging environment that we have, R&D and commercial, all in the cloud, and how do we keep them separated, yet how do we empower our scientists to be able to do all this new cool stuff in the cloud? We have this global footprint, which also makes it very, very tricky for sending our data from on-premise, from our wet labs, into the cloud. But the good thing is we have a cloud-first strategy. And that's just not our CIO saying we have a cloud-first strategy, but we have about 50 or 60 people now attending reInvent just to learn. So IT people, data scientists, engineers, and actually bench scientists are here to learn how they can do their data processing in the cloud. So this is a big thing for us, and we really fully believe in AWS. As you know, the biotech lab environment, if you're in this room, you know what it is. It's very, very complicated. It's very hard to put into the cloud. It's all this really, really messy, wet, experimental stuff. Yet we want all this data to move from one location, centralized to the cloud, so make the processing much easier. However, if you walk into a lab, you'll see, at a startup, you'll see dozens, hundreds of instruments. If you come to Celgene, you'll see thousands of these things. And my last company, we supported over 10,000 lab systems. And the corporate side of me says, can't we just standardize, right? If you go into any chemistry lab, you'll see a bunch of HPLCs, Allergent, 1100s, 1200s, different firmwares, different connectivity, and whoever bought the scientist, they'll have a different licensing, so they have a different version of the software, and each individual scientist will save the file slightly differently. So it's very, very hard for us there's no such thing as a standard in the lab. And of course, we have dozens of sites around the world, and every scientist does things slightly differently. So even if two scientists are using the same instrument, they could be doing things completely different with the same instrument. For instance, if they're doing a little plate reader, they can have a different plate layout, different dilutions in the plate, and it makes really things difficult when we're trying to standardize that data. And storage and networking, officially I came from corporate IT, and we could provide some storage to our research scientists, but we were a cost center, so we were only given a certain amount of budget to be able to provide to our researchers. And if a researcher comes along and says, I could use 50 terabytes a week, I'm not budgeted for that. Yet we still have to support that, and that's our job as IT professionals, to be able to support our scientists. So how do we do it? So ultimately, we want to move our data to the cloud, and to not only just to move it for archiving purposes, but we found a lot of our scientists were trying to get around IT, and they have a job to do. They have data, they need to process it, but we as IT were not able to provide them petabytes of storage. So they just save data locally. I'll just save it locally, not tell IT. They wouldn't tell IT until the lab systems crashed. And 5 years down the road, I get a phone call, how come you didn't back up my PC? I didn't know you had data on there. So times 1,000, we have a huge problem in our labs. We estimated we have approximately a petabyte of hidden data in our labs. And right now we have a project ongoing to scoop all that up and move it to AWS. So that's one of our huge projects right now. And then once it's in S3 or another storage tier, we can put that into tiering. We can, S3IA, we can cold storage in the Glacier to make it even cheaper. And interestingly enough, once we centralize that, we can now make that available to our data science teams who can do data analysis and AI. And Pascal's going to talk about that later, about how we can do that now that we have the data in the cloud. Now, it's very, very hard, of course, to move that, not only because our labs are a challenge in themselves, but the applications. Some of our applications go back 20, 30 years, and some of the vendors don't exist anymore. Celgene isn't that big, so we can't go to Agilent and say, give us a cloud version of your software. That's just not going to happen. We estimate about 1% of our applications are cloud aware, and those are our NGS workloads. However, all those applications, they're hard-coded to save their data to a vendor's bucket. They won't allow us to save our data to our bucket. So it can be challenging working with other vendors. And also, we don't want to change our scientists, right? They went to school. They are, it is their job to invent new products and new cures for therapies. We don't want to say, you have to do this because we're IT. No, it's our job to help them do what they do best, and that is science. And we do have a problem with, a challenge anyways, with data transfer. We are generating terabytes and terabytes every single day. Now, how do we move that to the cloud? And I'll show you how we do that coming up. But real quick, this is really not a sales pitch. I know it starts off like that. But why do we use AWS storage? How come we're not just buying servers on premise? One, for us, it's a huge benefit has been no maintenance. When you upload your files to Amazon, they take care of that. We don't have to patch it. You don't have to deal with antiviruses. Oh, you still get those emails. System X is going down this weekend for upgrades. Well, we don't have that problem. It's also great value. We cannot beat the cost of S3. It is so incredibly cheap relative to what we do on premise. We've gotten some pushback. We have some large projects that do petabyte scale. And when we quote them what we think it would cost to do that on premise, they're like, okay, we're good. So some of our workloads, the storage alone is over $100,000 a month. But when they see the multi-million-dollar quote they get from corporate IT, all right, we're good. We believe you. Another benefit, we didn't anticipate this when we first started in our cloud journey, is integration to cloud services. So I started in the cloud a long time ago, and the cool things like Athena and SageMaker didn't exist. So it was just, AWS was just the infrastructure play, but it's matured so much that we can do all this new cool stuff just by having the data there. So not only do we support the primary use cases and the computation, but our data science teams can do so much more with it because it's centralized and the Amazon environment has these new cool tools. And of course, you'll see a lot of slides that say AWS storage is infinitely scalable. And that's absolutely true. And you can consume and spend as much as you can take. However, what's more important to this is that's really on there. It's infinitely scalable immediately. Right? So not too long ago, we had a scientific project come to me and say, Lance, we could use 100 terabytes of storage. And we were thinking, we could do that. We could do that. But what if their estimates are wrong? And it was. That 100 terabytes was really 200 to 300 every quarter. And that was for one collaborator out of 5. So that quickly turned into that 100 terabyte request turned into a couple of petabytes. And if we could turn that around in 2 months, that would be great. So there's no way we could do that on premise. In the cloud, we have this ability now with this that we can really operate at the speed of science. IT is no longer the hindrance. If someone needs a petabyte, here you go, done. You just got to pay for it. Storage options. So this is how we see storage at AWS, and this is our preference. There's actually an order here. So our first preference, we push people to S3 because it's super cheap, has a lot of security built in, has very, very high bandwidth. It is kind of high latency, but it can work very, very fast. We have large clusters that go to 8,000 nodes simultaneously accessing petabytes, all from S3. It is higher latency, so it takes a little bit of getting used to. But it's object storage. And a lot of traditional IT people have a hard time grasping what object storage is. It is different. And a lot of on-premise people are thinking, I can just click on a link and it pops up. Well, object storage just isn't like that. You can't do a file edit. I want to edit a file. You can't do that. You have to download it, edit it, and then put it back. So it works very, very differently. So if we have a workload that can't use S3, our next option is EFS. So this is a managed NFS type service. You just mount it on your Linux workstation or your EC2 instances, your VMs, and it just works. You don't have to do anything with it. There's a EFS IA tier now that you can save about 90% on the cost. So there are some cost-saving options there. However, it is a Linux option. If you have Windows workloads, FSX for Windows works reasonably well, integrates with the Active Directory. And if those three don't work, and we have a couple of use cases, we will then use EBS storage. It's a block storage that you can attach to a machine. You can have any type of file system. However, you have to make the file system. You have to do your backups. You have to maintain the EC2 instances. If they go down, someone has to go and fix them. So that's why we prefer the first three, but there are some use cases where we have to do EBS on EC2. Now, there are two options here that I didn't list. I'll go over them. There are edge cases. So for instance, ephemeral storage. So many of the EC2 families have SSDs directly attached to the hardware. They have a tremendous, hundreds of thousands of IOPS. However, if you're an EC2 expert, you will know that if you stop your virtual machine and when you spin it up, it could spin up on the other side of a data center. And the SSD that's attached to the hypervisor doesn't move. So if you save data to ephemeral storage and you turn your server off, you're going to lose all your data. However, it's very useful for scratch storage, so we use it for our NGS workloads. We use petabytes and petabytes every day. However, we don't use it for any sort of long-term storage. Not dissimilar is FSX for Lustre. It seems like it's the same thing for FSX for Windows. However, how it works is it grabs a copy of the data from S3, brings it to the cluster, presents it to a large HPC cluster. You can hit it with thousands and thousands of IOPS, and at the end of your computation run, it'll put the data back into S3. So it's not intended for a long-term storage. It's intended for a very, very fast NFS experience, but you have to have the Lustre client. So when we first started going with the cloud, our journey, I started the company, and I had proposed to a project that we don't go out and buy a petabyte of storage. We should just use the cloud. My first thought, in the first glance, we're not putting our data on the internet. Are you nuts? So there is a bit of an organizational aspect to the slide. And so there are multiple layers when we put data into the cloud. It's not just putting it on the internet. There's a lot of protection in place. So how we are organized at Celgene is there are multiple project teams. So a particular department or a project, they'll have a small, as Amazon parlance, a pizza team that is reasonably self-contained. They have all the experience and knowledge to create a particular platform or a project. So they go through their architecture, all their own programming. If they need some database help, that's all self-contained within that project team. Now, on top of that, or with them, is the cloud team. So we make sure that they have good architecture, they're adhering to security practices, work very, very closely with the networking and security department. So there are certain services and certain functions that we blacklist that we don't allow individual projects to use. So for instance, we don't allow people to open up a VPC to the internet. It's just not allowed. So we make sure that all security rules are followed. And of course, and then on top of us, or below us, depending on your point of view, we rely heavily on the AWS services for security. So most of our computations take place within a VPC. None of our VPs are internet facing. They can only be accessed from on-prem. So if there's a bunch of servers, they can't be hacked by the internet because, well, they're not on the internet. So to get them, you have to come to our company network, go up the fiber connection, direct connect, into our VPC, and they're completely isolated from the internet. We also use Security Hub to do AI scanning on our logs, et cetera. And the Security Hub has a tremendous amount of data that we don't have access to, for instance, flow logs. Some of our accounts have flow logs on, some of them don't, but a Security Hub will see a bad login attempt from a particular location that we normally don't come from. And it'll let us know that we see some bad logins. Maybe you should do something about that. We also have a lot of data encryption, new GDPR workloads coming online. And depending on the storage subsystem, you can enforce via policy encryption. On premise, we have paper policy, you have to encrypt, right? But you can hard encode that in the cloud. You can say if your data is not encrypted, it cannot be uploaded. And of course, we rely on AWS. And the automation that we use as the cloud team is a company called Turbot. So we have automated processes that will see what people are doing. So someone creates a bucket. That's my next slide, I believe. Yeah. So these are some of the rules. You don't have to take a picture of it. There we go. So on the left-hand side there, these are some of the policies that we have depending on the workload. So if a GDPR workload comes along, we'll put some of these policies on that account. And if they create a bucket, automation automatically picks that up, applies these policies, and they have to encrypt. On the right-hand side, for instance, we can put on our bucket policies that the bucket can only be accessed by a particular VPC. It can be accessed only by a certain IP or VPC endpoint, depending on what the workload needs. And in the middle, we have a couple of workloads where users use S3 as their home drive, so we have to keep people, their workloads separate from others, and that's the bucket policy we use for that sort of thing. There are, of course, the storage itself is one thing, but how to get the data to the cloud, and that's what the remainder of the talk is about. So if you were going to use S3, one of our top areas that we use to transfer is the storage gateway family, which includes data sync. So a storage gateway is an appliance that you can buy or download into VMware, put it on your local network. It presents a network share. From your user's point of view, it looks like a Windows share. You save your data to it, boom, pops up in the cloud. Same thing with data sync. The difference is that it uses an existing network share. The benefit of that is you can have a larger share. If you are coming from an organization that isn't quite object aware yet, but use SFTP, you can use the AWS transfer for SFTP. Data will automatically go into your bucket. Now, the next couple of options there, it's a lesson learned that you guys can take away from us. We thought this was going to be the way that we would transfer data to the cloud. It didn't work out so well. So we thought, because we're cloud experts, we kind of know what we're doing, right? This is what we normally do. And our data engineering teams are like, great, we use the SDK, the CLI, or some sort of GUI to transfer data to the cloud. But when we rolled out Cloudberry and some other GUI tools to our end users, it did not take. And we tried for about a year. Like, you should use this. This will get your data to the cloud. And the concept of object storage to our end users was alien. And after about a year, we were like, maybe we should try something else. This is definitely not working. On the slide, you'll see something that is crossed out. And some people do it. We will caution you very strongly to not do this. It is an option, but please do not do this. That's some sort of fuse mount or mounting an S3 bucket as a file system. And 10 years ago, that's what we did. We thought we were being really cool, that you could have a mount point on Windows or Linux and just mount a bucket. The problem with this, how these work, is they'll take your entire bucket listing, put that into memory, and if you want to edit a file, it downloads the file, puts it into memory, you make your edit, and it re-uploads it, all unbeknownst to the application. And if you're a small business and you have a little Excel file, that's fine. But our buckets are now hundreds of millions of objects. And when you try to cache that hundreds of millions into memory, that has a huge overhead. And then our genomic files are 30, 50 gigabytes each. This client is going to try to put that in memory. And about a year ago, we finally convinced some of our clients not to do that anymore. The servers that had mounted these were crashing every 5 minutes. It was so bad that we had a cron job just to restart the service. But we finally convinced them not to do it. And it's not that it's unstable. You will almost guaranteed to have some data loss. If two clients have a bucket fuse mounted, one will make a change, the other won't see it, they'll try to make a change simultaneously, and they'll step on each other with that. Transfer acceleration is not necessarily a method, but it's an additional option you have to transfer data from across the world to a different bucket. So you turn this feature on, and you have a different address for your S3 bucket, and you use the S3 backend to transfer your data to a bucket, and it doesn't have to use your company's network. And the Amazon network is faster than ours, so it definitely helps. About, for long distances, maybe a third to 50% improvement in transfer time. If you're using EFS, again, the data sync client will work reasonably well. And there's also just digital mounting your EFS file system from on-premise. You just rsync it up. Same thing with FSX. FSX also supports Storage Gateway. If you're running EBS on EC2, the traditional Unix or SMB copies from Windows work just fine. Snowball, we use Snowball for transferring large data where time isn't necessarily a hindrance. So when you put in an order for a Snowball, it takes at least a few days to arrive. You set it up, take it to your data center, spend a couple days copying your data over. You close it up, the FedEx person shows up, and you send it off. So it's a minimum of about a 2-week process. But each device can hold up to 100 terabytes, so it can be good. If you're, if you're trying to send some data over a T1, that's just not going to happen. Some other ways to do it. And we used to use third-party projects or products to copy data, Aspera and the NetApp. We had some issues with that, and we no longer use it. But if your organization uses them, they will absolutely work. We found that a lot of these tools will require an EC2 instance to be stood up in your account, and it works with some sort of virtual machine on your local network and then transfer the data back and forth. However, a lot of these tools will encapsulate your data within some sort of proprietary binary. So they will say, we will put your data in S3. That is absolutely true, but it can only be accessed by this particular client. If you're only doing a couple files, that's fine. But if you're doing it with 8,000 nodes, that one EC2 instance will become a huge bottleneck. And it's additional expense and maintenance that you otherwise don't need. Now, getting your data to the cloud, it can be easy. It can be very, very hard. We do a lot of work with startups and academics. And we see that the smallest companies that we work with all go over the internet. But if you're in this room, you're probably a biotech, pharma, and that's not secure enough. Right? Generally, if you're going over the internet, security is by IP address, maybe some sort of login. And we don't, for us, that's not secure enough. So we see, once companies start to mature in the cloud journey, they'll do a VPN connection. So it still runs over the internet, however, there's the IPsec tunnel between Amazon and yourself. That encrypts all the data, and it hides it from the bad people. Of course, there's the big kid in the room, the Direct Connect, and we strongly recommend this. It comes in different flavors. If your organization is looking at Direct Connect, they come in two major categories, how we put it. Less than 1 gigabit and 1 gigabit and over. And it seems like, 1 gigabit is just 10 times the 100 megabit, right? It seems like that, but that's not the case. Anything less than 1 gigabit only has one virtual interface. And if you're a network nerd, that will mean a very big deal, because right off the bat, you're going to need at least two. So if you buy a 100 megabit connection, you'll need 200 megabit connections. Now that alone is more than the price of a single gigabit connection. A gigabit and a 10 gigabit connection comes with 50 virtual interfaces. You're wondering, what's a virtual interface? Every VPC that you create will need a virtual interface, as well as you'll need a second or more interfaces for public services like S3. Now, if you have transit gateway, there's other topologies that you won't necessarily need more than a few, but you're going to need at least two. So that's why we recommend 1 gig and up, and you also get the additional benefit of having faster speed. This is how we connect. So like I said, we are a global company with sites all around the world. I think combined we have about 100 accounts and about 200 VPCs, give or take. And different workloads will work with other workloads. So we separate out our accounts into different projects and departments. So one department will have their cost center, their account, their VPC, but they work very, very closely with another department and their VPC. So they need to exchange data. But they may be in different regions. So we have, our network, we have a VPLS mesh that combines all of our sites. So any site can get to any VPC at any different region. And so if we were to do this from a point-to-point, a direct connect for each site, we would need over 30 direct connects instead. We don't want that mess. So instead of every site having a different connection to one of the regions that we use, they just connect to the mesh. And we have an Equinix Colo facility where all of our network gear is. And we have a connection from the Equinix facility to Amazon. So you see on the slide here, the sites at the bottom, they connect to a little mesh there, go to our customer cage. We have maybe a few 100-meter fiber optic cable that goes to the Amazon cage, and then therefore goes into the Amazon network. And you see the two purple icons at the top, one for the public endpoints and one for the VPCs. But we have many, many VPCs, so on the right-hand side, you'll see a lot of those. And to bring it all together, this is how our architecture looks like from on-premise all the way to Amazon. So on the left-hand side, you'll see our research scientists. They go to their bench, do their experiment, load some plates, go to the laboratory PC, hit file save, do some preliminary analysis, what have you. And that's all they know. That works. And then from then on, all the automation kicks in. When they hit file save, it goes to the local file server. And for us, that's a NAS device, a NetApp. We specifically picked the NetApp. We didn't pick a Windows server. We didn't pick a Linux server, because NetApp supports multiple protocols on the same share or export. So that's a huge win for us. We can have Apple, we can have Linux, we can have Windows, all work off the same directory. And then those files are then picked up by our data sync application that's running on a VM, which then moves it up with the AWS data sync project or the service, and it pops it directly into S3. Now, you could also use storage gateway. So we use a NetApp also because it's big. All right, so our NetApp is over a petabyte, multiple controllers. It's redundant. But if you're only doing plate readers, HPLCs, you don't quite have the NGS workloads. You don't need to have a large petabyte system. You can get by, and a storage gateway maximum size is 16 terabytes. So if your workloads can fit that within a day, you can absolutely do that. And it's far easier and cheaper too. Anyway, so once our data gets to S3, it can kick off all these other workloads that we have. So we have some users using Athena for Spark queries, SageMaker if you're doing AI, all in the same bucket. And of course, our CROs on the top. We struggled in the beginning working with our CROs. They only wanted to FedEx hard drives to us. And then we said you should really go to S3. And 80% of our CROs now support S3. They send it directly to our bucket, and we're happy. We have a couple that are kind of resisting, but they support SFTP. So we don't have to maintain an NFS server or any FTP server for them. We say, here are your credentials, and you can automatically upload into S3, but you don't have to be S3 aware. And with that, next up will be Pascal, and he'll talk about digital pathology with the data that we have in S3.
Thank you, Lance. Good afternoon. My name is Pascal Staring. I'm the IT Director for Translational Research at Celgene, now BMS. The infrastructure that Lance just outlined and that we built at Celgene enables us to share information and data with our colleagues and collaborators all over the world. And one of the applications that takes great advantage of that infrastructure is our digital pathology. Pathology is mainly concerned with phenotyping or classifying tissue and cell types of patients. And the workflow that we have created is the images are stained and labeled. So you apply a color to highlight the tissue or the presence of a molecule in a cell in the image. This assay development happens up front, and the images are then scanned typically using a microscope, and these stains will show up in different colors. We combine these colors in an image where we can investigate what has been labeled. Typically, multiple pathologists, experts in reading these images are involved in analyzing the state of the sample and therefore help determine the course of treatment for the patient. And depending on their availability, they can be all over the country. So not too long ago, less than 2 years ago, we would save these images on a disk drive and ship them to the pathologist. That would take about 2 weeks, and then we would have to create a session with them where they would all look at the images, and then in a collaborative session, they would analyze the images. Of course, with the infrastructure that we have now, we can bypass that shipping of the hard drives to the pathologists, and basically directly from the microscope, we upload them to an S3 bucket, and then we bypass that step that takes about 2 weeks, which is time that is critical for the patient. And pathologists and experts all over the country can now collaborate real time with special tools that are available to manipulate the images, not just to look at them, but to pan, to crop, to zoom in, to annotate, and to analyze these images. Oops. So what I'm going to explain here is what can we do next? So now we have these images with the pathologists. Can we do more? For example, can we help them in predicting the phenotype of these tissues and cells? Now, I must highlight that what I'm about to explain here is a very simplified process of a larger effort that we do at Celgene, where the scope of the analysis and research is much broader and deeper than I'm explaining here, but the approach is kind of the same. So what we want to do is, on the top left, you see a raw image. We want to find the cells in this image. We want to do a segmentation, and then the regions of these cells, we want to extract some features. We have about 130 plus features that we have defined for each of these cells. And we want to know if we can use that to teach or to create a model that can help us in phenotype prediction. So one approach is to use commercial software. So every vendor will ship you commercial software that will help you with segmentation of cells in an image, but they take the middle of the road. So they're not specific to the cell types you want to see. In general, they overestimate the number of cells, the cell boundaries are too wide. So what we want to do is, can we create our own process based on machine learning and adapt that to our cell types? So how could AI aid in the process? So what we're looking at is natural object segmentation, where there's a pixel-wise assignment of a class to these pixels to identify the objects. So on the left side, you see a famous image of three object classes. One is the person, one is the bike, and one is the background. On the right side, you see a different type of cell image that we have fed through our algorithm, which is a pixel-wise classification algorithm, which is explained in much more detail in other sessions, to arrive at an output that outlines these cells. So why do you want to use deep learning for image analysis? I thought this was a kind of a fun slide to look at. If you look at the error rate over the years in image analysis, before 2012, before machine learning became to the stage, it was all based on classical computer vision, and these methods had an error rate of about 20 to 30%. Once we introduced machine learning and deep learning and learned how to use it and how to improve on it, you see these error rates drop drastically, and in about 2015, it started to become a better than human classification. So that's why we want to use that. If we look at the images that we want to process, there's a few challenges that we have to take into account. One of them is there's so many different types of cells that we want to image, so many different types of experimental conditions, that it's hard to find the training data. Be more specifically, to find the ground truth of these image types. Granted, there are now lots of teams that are looking at this in the world, and they are publishing the efforts around this. So more and more ground truth becomes available for these types of images. The pixel value variation, the gray value, is also a concern. These are 16-bit images, and basically you see cells in the deep dark to the bright gray. Another typical issue with tumor cells is that they tend to cluster, so there is not enough background to segment them away from the background and identify the cells. And the last one that we need to take into account is the sheer number of cells. As you can see here, there's thousands of them. So the first thing that we tried is, what about all the models that are out there that have been trained? So we tried a mask RCNN, which is a region-based convolutional neural network with a ResNet-50 backbone. And as you can see, the results are kind of disappointing. It doesn't find all the cells. It cannot separate the cells that are touching. But it's actually not that surprising, because it wasn't trained to do this. So we had to do this ourselves. And the tools that we use SageMaker, and then the tools within SageMaker is scikit-image, which is a Python-based image processing package, OpenCV, which is an open source computer vision library of classical image analysis algorithms, and PyTorch, which is the Python machine learning package. So if we look at the segmentation, we kind of divide it up in two steps. This is, again, this is a simplified approach. The first thing that we apply is a semantic segmentation using UNet, which by itself is a CNN-based segmentation for medical images. And this is to separate the cells from the background. We do not separate the cells when they are touching. And then the next step is a cell detection using a faster RCNN algorithm, which is, since it's a region-based, it draws the bounding boxes around the objects. These two together we combine to create the mask of the cells. So this is the result of the segmentation. So on the left side, you see the image that we used in our example, and on the right side, you see the result. Yellow is cell, purple is the background. The fastest RCNN detection draws boundaries around all these cells. Now, this is hard to see, so if you zoom in a bit, you see all these bounding boxes around the cells. If you take a closer look, you actually see that it finds the cells that are touching. It will separate those out based on the characteristics of the model. Now, these two together, the object mask and the bounding boxes, we combine using a marker-based watershed to find the actual outlines of the cells. And on the right side, you see the results there. Now, if we compare that to the vendor software result on the left side, and I don't know which one is better, so I asked our scientist, and if you zoom in a little bit, you see that our cells are more uniformly shaped. The vendor cells are bigger, there's more of them, so there's more false positives. Now, sometimes cells aren't round, so it's not a good thing to find round all the time. But if you look at these highlights in the red boxes, you see the difference between the two methods. In this case, they find the same cells. I think that the cells that we find have a better boundary. So now that we have the masks, we're going to extract the features based on these masks for these cells and then feed that into our machine learning to do a phenotype prediction. So the tools that we use there are simple. It's again in SageMaker. We use pure Python and the scikit-learn package. And I'll go back to this image. This is actually our test image where we have a population of cells of which some of them are CD3 positive. And we put in a label. So what we're asking the machine learning to do is based on the features that it created, point out which cells are CD3 positive. So all these features are being extracted for every region of the cell that we find. So this is a very sparse image. You have to remember what we showed in the previous slide where we have many, many, many more. So 130 plus features for each of these regions, and we fed those into a number of machine learning algorithms, and we ranked them based on the accuracy compared to what a human would classify as a CD3. Now, this by no means is optimized, but you can see that the first four methods have an accuracy of 95% or more, which is amazing compared to what we had before with computer vision. So the lasso regression algorithm seems to perform the best. The final step that we did was, okay, so if we do this using principal component analysis, or TISNE, which of these features actually contribute the most to the accuracy of that 96%? So we've rank ordered them, and it turns out that the first 10 or so have the biggest contribution in this accuracy. So you can do a trade-off in terms of computation effort to calculate all these features for every cell with a little bit of accuracy and be much more effective. So here we have it. We have all these images that are being delivered to the pathologists anywhere in the world who can access these images. They have tools to look at them. And on top of that, we can highlight these images. We can annotate these images with regions of interest that say, hey, this is a part of the cell that is highly positive for, in this case, CD3, that might, you might want to take a look at that. I can see in the future where the role of these algorithms are become much more prominent, in that it will only involve the pathologist if there's an issue that has been detected, and for all the other analyses, it will take the machine results. So that's where we are at this point. I'm going to hand it over to Sam. Thank you.
So thank you very much. And I would like to remind you of the other life science sessions that we have, as well as there's the Healthcare and Life Science Lounge at the end of the hallway, and then you take a left. And we will be there afterwards to answer questions as well. But we also have the opportunity, we have a microphone set up here, and I'll run around on this side of the room, and we are available to take any questions of the audience right now. So if anybody has any questions, we're happy to answer. Raise your hands. Okay. There's a microphone right up here if you want to come up, or just that way everybody can hear you if you don't mind. Thank you.
Hi, quick question for Lane. Your architecture didn't have databases at all. Are you using databases, Redshift, or stuff like that? Do they play a role as well?
Yeah, we're a big proponent of database as a service as well, so RDS. We have a number of workloads using, RDS MySQL, a little bit of Aurora, depending on what your needs for recovery are. We have, I think, a couple use cases on MariaDB, which is functionally equivalent as MySQL. And we also have a few workloads using Dynamo, but within Discovery, we don't have any Redshift. I think our sales folks are using Redshift. But today's topic was primarily on getting the file data out of the labs. But we are using some database services.
Any other questions? Okay, like I said, I do encourage you. There is the Healthcare and Life Sciences Lab. We'll be down there to answer any questions or just generally meet everybody. Once again, I just really thank you all for coming and listening, and have a good evening. So.
Okay.